In this video, we'll be discussing our second case for partial fraction decomposition, which is when we have a linear factor in the denominator that is repeating. The form of a partial fraction decomposition for a rational expression containing the linear factor ax plus b occurring n times as its denominator is p of x equals ax plus b raised to the n power, and then we get this line of fractions here, which again, I think it's more complicated than what it really is. Basically, what we're going to do is we're going to take whatever this linear factor is, kind of ignoring the exponent, and we're going to put it in the denominator the first time to the first power, the second time raised to the second power, the third time raised to the third power, and we'll do and so on until we hit whatever that n is. So if it's only a squared, well, then we're only going to have two fractions. We're only going to raise the ax plus b to the first power and then to the second power. But if that linear factor is to the fifth power, well, then we're going to have to write it out to the first, second, third, fourth, and fifth, creating 5 fractions. So even though the degree of the denominator may change as we're adding exponents to this linear factor, the numerator is always going to remain a constant. So again, I'm going to opt to use A, B, and C instead of the subscript notation. We want to find the partial fraction decomposition of 3x squared plus 49 over x times x plus 7 squared. This example is actually a combination of case 1 and case 2. We have a linear factor x that does not repeat, and then we have a linear factor of x plus 7 that does repeat. This is actually going to take 3 fractions. We're going to have one fraction with a denominator of just x with a constant numerator. Then we have to deal with the repeating linear factor, where we're going to start with just x plus 7 raised to the first, and then we're going to build up to that x plus 7 squared. 3x squared plus 49 over x times x plus 7 squared is going to be equal to, so our first denominator is just x, the next one's going to be x plus 7, and the third one is going to be x plus 7 squared. The factors in the denominator are linear, because again, we're kind of ignoring that squared there. I know that makes it quadratic, but the original factor was linear. So that means that our numerators are going to have to be constants. I'm going to call them A, B, and C. Once you get the setup done, all of these are really the same. We're now going to multiply through by the LCD to clear the fractions, which is the same as our original denominator. That'll give us 3x squared plus 49 equals A times x plus 7 squared plus b times x plus 7 plus c times x. Now we're going to multiply everything out on the right-hand side, combine any like terms, and then we want to start grouping things, like get all our terms that have an x squared together, x's together, and then our constants together. For this x plus 7 squared, we're going to have to write that twice and multiply it out, or use our squaring a binomial shortcut. We get x squared plus 14x plus 49. Distributing my bx, this is going to be bx squared plus 7bx plus cx. I got to distribute one more time that a. And now it's time to get things organized. which is the same as rewriting it in descending order. I want to put my x squared terms first. And sometimes I find it's helpful to kind of cross them out because there's a pretty long list and I don't want to double count something or miss something. All right, terms with an x comes next. There's actually 3 of them. 14ax plus 7bx plus cx. And then we have our plus 49. Oh, that should be a 49a. I'm misdistributing my a. Okay, 49a. On the right side, we're going to want to factor our x variables out so that we can equate coefficients. But notice on the left side, we're missing a linear term. There's no x to the first term. I want to put a placeholder in there so that when I equate my coefficients, I have something to equate with. This becomes a plus bx squared plus 14a plus 7b plus cx, and then just plus 49a is all by itself. We're ready to equate coefficients and write our system of equations. So 3 has to be equal to a plus b. 0 has to be equal to 14a plus 7b plus c. And 49 has to be equal to 49a. Now, if any of these were negative on the left-hand side, I would, of course, take that negative with me as I'm writing my system. So let's write up our system and solve. Now this one's going to be pretty easy to solve. Since 49a equals 49, we know right away that a is equal to 1. I'll plug that into my first equation and solve for b. A plus b equals 3, so b is going to have to be equal to 2. And then we'll plug both of those into our second equation and solve for c. So we got there 14 plus c equals 0. So c has to be negative 28. Now that we have solved our system, we're ready to plug these numbers back into the numerator of our original statement. So 1's going in for A, 2 is going in for B, and lastly, negative 28 is going in for C. And then that'll be our final answer. 3x squared plus 49 over x times x plus 7 squared is equal to 1 over x plus 2 over x plus 7 plus negative 28 over x plus 7 squared. I left the negative in the numerator. You could put it out in front, but if your numerator ends up being more than one term, be sure to factor that negative out if you want to put it out in front. In the next video, we'll talk about how to handle a partial fraction decomposition when we have a prime quadratic factor in the denominator.